decomposition reactions. Now, decompose means to break up. So, the very name of the reaction implies breaking up of a molecule or a substance into simpler substances. So, let's take an example. If A, which is a big molecule or which is a big substance, breaks up into smaller substance, this is decomposition reaction. Now, to break the substance A, energy is required. And this energy may be in the form of heat, it may be in the form of light, or it may be in the form of electric current. So, whichever, depending on the three types of source of energy, we have three different types of decomposition reaction. So, first, let's take the definition of decomposition reaction. The definition is when a large substance breaks up into two or more simpler substances. I'm sorry, I've changed the color of the chalk. So this is what a decomposition reaction is. When a big molecule or a bigger substance breaks up into two or more simpler substances or smaller substances, it is a decomposition reaction. Now, because energy is required, so decomposition reactions are endothermic in nature. Most of the decomposition reactions are endothermic in nature, that is, heat is absorbed. So, first type is the source of the source of energy is heat. So, this is thermal decomposition. A glaring example of thermal decomposition, which is oft asked in CBSE examination and other examinations also, that is decomposition of ferrous sulfate crystals. FeSO4.7H2 called green vitriol. When they are heated, now this implies 7 molecules of water of crystallization. So when they are heated, first of all, FeSO4.7H2 breaks up into, now this triangle below the arrow implies heat is given. So this breaks up into FeSO4 plus 7H2O. Okay. So these are the 7 molecules of water crystallization which you will see on the test tube or wherever you are heating. So and if this is carried on further, then FeSO4, it breaks up into Fe2O3 plus SO2 plus SO3. This is it. This is pale green in color. And this is somewhat reddish brown or light brown, you can say, or light yellow. And these gases give the smell of burning sulfur. So this entire equation is to be given whenever decomposition of ferrous sulfate crystals is asked. This equation is very, very important. Then next you have decomposition of lead nitrate. These are white, this is white powder. And on heating, it converts into twice PbO plus NO2 plus O2. This is a reddish brown gas. This is actually, you can say, this is litharge, you call it litharge. The characteristic of litharge is that it fuses to the test tube. So if you have to take out litharge from the test tube, you'll have to actually literally break the test tube. So this is decomposition of lead nitrate. And oxygen, you know, is a colorless gas. Then you have decomposition of calcium carbonate. It's a reversible reaction. Calcium oxide plus carbon dioxide. So these are some of the thermal decomposition reactions. Then we have decomposition by light, which is called photodecomposition. And here we'll be discussing the decomposition of silver chloride, let's say. This, on exposure to UV light or sunlight, it breaks up into silver globules. Plus chlorine gas. Now chlorine gas is a yellowish green gas which comes out. Another example of this is silver bromide. In the presence of sunlight again, it breaks up into silver globules plus bromine gas. Bromine gas here is reddish brown in color. It has reddish brown fumes. Now the question which is asked in this case is, why are silver salts and hydrogen peroxide and many such compounds stored in dark colored bottles? And the simple answer is to prevent their photodecomposition. So to prevent the photodecomposition, the answer is to prevent their photodecomposition. Then the next we have is, next in the line is electrical or electric decomposition, when the source of energy is electric current. And the most prominent, actually all the electrolytic electrolysis, wherever electrolysis takes place, all these are examples of electric decomposition. For example, electroplating is there, electrorefining is there, all these are examples of electric decomposition. But let's discuss the electric decomposition of water. So we have here, let's take a beaker. Let's drill two holes in this, and let's attach two nails in the holes. Now these nails will actually serve as the electrodes. Okay, attach it to a battery. Then add some water to it and invert two test tubes full of water over these nails which act as electrodes. On passing electric current, you will notice, now this is the positive end, this is the negative end. On passing electric current, you will notice that now bubbles evolved on the cathode, that is this side, are double the bubbles evolved on the anode. These are lesser in number. So this is hydrogen here. Hydrogen is evolved on the cathode, and oxygen is evolved in the anode. And the reason why the number of bubbles or the amount of bubbles evolved on oxygen are less, or just half of the bubbles evolved on the cathode, or the test tube which is placed on the cathode, is because in water, if you see, the volume of hydrogen is just double the volume of oxygen. So number of bubbles on the in the test tube rather, which is placed on the cathode, is just double the number of bubbles evolved on the test tube placed on the anode. So this is electric decomposition. Another case of electric decomposition, in fact, this is photo decomposition only. I forgot to tell you there. And that is a very prominent reaction which occurs in nature all the time in the plants. That is photosynthesis. It's an example of photodecomposition. You have carbon dioxide and you have water in the presence of sunlight and chlorophyll. Now, chlorophyll is a photoreceptor. Glucose plus oxygen is formed. So this is again a reaction which depicts photodecomposition.